Hey students, Friday here. For our next plate of lunch, we want to investigate what happens when chunks of our crust move away from each other and how scientists used creative use of technology to piece together the evidence. The chunks of crust are called plates, and where two plates meet, it's called a plate boundary. We're going to start off with a quote from literature. This might surprise you, but I think it will help you to understand the nature of this plate boundary. Two roads diverged in a wood, and I took the one less traveled by, and that has made all the difference. What does the author mean when they use the word when they say that the roads diverge? What does diverge mean? When two roads diverge, they split. What Robert Frost was talking about was choice in a free society and how, in his opinion, he felt like it was better for us to make individual choices about things. We can also apply that word to our next plate boundary, divergent plate boundaries. When two roads diverge, they split. When two plates diverge, they are also splitting in these divergent plate boundaries. When this happens, when they diverge, liquid hot magma becomes lava on the surface, can fill the gap, and it creates new crust. This is a really interesting story for you to learn about because there is a long series of uses of technology that we have used to understand the nature of plate boundaries. One of the things that we always want to keep in mind when we're learning about motions of crust on the surface of the Earth is that it is a very slow process. This is happening over thousands, tens of thousands, hundreds of thousands of years. So scientists and engineers have to be very creative with how they make measurements here to show that this is the reality of what is happening with these plates. This is all based off of evidence. And to understand that, we kind of have to understand how technology has changed over time. And we've really used two main ways to collect this evidence for divergent plate boundaries. We have the modern way and the old-fashioned way. And I'm actually going to start with the old-fashioned way because I think it's really interesting how people have used the development of technology over the last 70 years or so to help us to understand divergent plate boundaries. And then I'll talk about how we use GPS on satellites in modern times to make this so much more easy. First, let's start by taking a look at some video of what is actually happening at a divergent plate boundary. So once again, we have a cutaway of the crust. We see that the crust is the grayish material on the top with two arrows this time pointing away from each other. And underneath we have the asthenosphere, the very top of the upper mantle. Let's see what happens when these plates are separating from each other due to those convection currents, the cycles driving the plates away from each other. So as these plates are separating from each other, magma from down below is filling in the gap, becoming lava on the surface, and as that lava cools down, it solidifies into new rock. At divergent plate boundaries, we are producing new rock, and that's important for us to understand because there is a interplay, a combination of two things that are happening with convergent and divergent plate boundaries. One thing that lots of students ask, and this is a great curious question, is, well, hold on. If we're destroying crust at convergent plate boundaries, wouldn't that mean we'd be continually losing crust over time? That would indeed be true if there wasn't also divergent plate boundaries. For every convergent plate boundary in which we're destroying crust, divergent boundaries are creating crust. So this is the basics of how divergent plate boundaries work. The crust is separating along the line in the middle. Magma, which becomes lava, fills in the gap and solidifies to become new rock. Now, let's compare this to some of the things that have happened with use of technology to understand what was going on. Because remember, these motions happen over thousands of years. Ain't nobody got time to wait thousands of years to determine what happens, and so we've had to seek other evidence of what's happening. And this video that you see is going to show how this divergent plate boundary in the middle of the Atlantic Ocean, where this little red segment is highlighted here, will show us how we have used old technologies to help us to understand what's happening. Let's talk a little bit about how that technology has changed before we see what happens with the divergent plate boundaries. So, we got to go back to submarines in World War II. One of the interesting aspects of human history is that human wars have frequently defined a lot of how technology is pushed over time. This is a British submarine from World War II, and with the development of submarines came the developments of trying to develop technology to find those submarines in an ocean. And submarines being threats to ships in World War I and World War II and into the modern era have resulted in the production of a technology called sonar. Sonar is a technology that is very similar to what we would think about with bats. Bats give off signals through echolocation that bounce off of objects so that they can detect what objects are near them or where bugs are to be able to catch them, because most bats are insectivores, meaning that they eat insects. Well, we sort of took a cue from that natural example of echolocation and developed it into a system called sonar. And sonar is basically a system that uses sound bouncing off of objects to determine the distance that those objects are away, as well as what their overall shape is. So the red lines represent sound waves coming out of the bottom of this ship that bounce off the seabed, and then we get a sound bouncing off of the seabed with these green lines that are captured by equipment on the ship that can tell us lots of details about what's going on with the seabed. Now, it wasn't just sonar that we used to answer this question, how do we know what's going on with divergent plate boundaries? We also had to send small, thick-walled submersibles down to the bottom of the ocean bed to collect rocks. Remember at the beginning of the year how we talked about how we can collect rocks on the moon, for example, when we landed on the moon 6 times between 1969 and 1972, and we learned a lot about the formation of the moon from collecting rocks there and analyzing them? We did the exact same thing with the seabed near divergent plate boundaries to gather evidence for what was actually happening there. Scientists don't just assume they know what's happening, they collect evidence to make sure that their understanding of what is happening matches what the truth would be. So these technologies all combined together to produce a picture for us of what was happening at divergent plate boundaries. Here's what we found out. We are focusing on this red line here in the middle of the Atlantic Ocean that is a divergent plate boundary. How did we discover that before satellites? Well, when we did this, we collected these rocks and analyzed those rocks and discovered something really interesting about their magnetic properties. Remember how we said that Earth has a magnetic field? The Earth has a north magnetic pole, the Earth has a south magnetic pole, and I want to point out in this example that the tilt of the axis of the Earth in this video animation is not correct in comparison to the magnetic pole. The Earth has an axis tilt at 23.5 degrees, but the magnetic pole is in a different location. And so this diagram is not entirely accurate, but that's why you have a science educator to help you to understand these things. So knowing that the Earth has a magnetic field can help us to analyze rocks that solidify. Here's why. Remember in breakfast we talked about how the outer core is cycling around and producing this magnetic field for the Earth? Well, as that liquid magma inside the outer core cycles around, it flips Earth's magnetic field every 15,000 to 150,000 years, depending upon how that liquid magma is cycling in the outer core. So when a rock forms under a particular magnetic field, we can compare it to rocks that form in a different magnetic field. And that is indicated on this diagram with these darker lines of crust versus the lighter lines of crust. What these different lines of crust represent, and let's go ahead and play the animation. The darker lines are representing a normal polarity. The lighter lines are representing a reversed polarity of the magnetic field. If these boundaries where there's a crack in the Earth didn't move, we would just expect to see rocks of different polarities just stacking up on top of each other. But that is not what we see. What we see is over time, as this plate separates, we get this reversal in the rock polarity. So let's play the animation. Rocks are formed under a normal polarity, they move away from the center of the boundary. Then rocks are formed under a shifted polarity as the Earth's magnetic field forms. And we have this light gray. Then they switch back to normal polarity. And so the original way that we discovered divergent boundaries was a combination of using sonar developed in World War II to map the surface of the ocean, and then actually going down there and collecting rocks and finding out what their magnetic polarity was at any given time so that we could have an understanding of what motions we would expect. If the crust wasn't moving, we would expect to see different polarity rocks just stacking up on top of each other. But what we actually see is as these two plate boundaries are separating from each other, we see normal polarity rocks, they move out of the way of the boundary, replaced by reverse polarity rocks. They move out of the way of the boundary, replaced by normal polarity rocks. They move out of the way of the boundary. So we see this banding pattern of magnetically aligned rocks depending upon what the Earth's magnetic field was like when these boundaries separated from each other. All right, how do we do this in modern times? Well, in modern times, it's actually way easier. Okay. I think it's really important for you to understand the history of these things, though, to see how technology both limits and drives science. In modern times, it's so much easier. We build relay stations on 2 different continents. We have many, many satellites orbiting the Earth, and every few days we record the position of continents, and then over a period of years we can see the very subtle movements that exist between the separations of these stations based upon satellites recording where they are on the surface of the Earth. So in modern times it's become a heck of a lot easier. This is a summary of what we've learned from the magnetic flipping of the Earth's poles and analyzing rocks. So if you are more of a learner who wants to read something rather than visuals, you could pause the video and read this. We also have analyzed fossils as well and get a better example of the fossil record, what that is telling us about divergent plate boundaries. So if plate boundaries weren't moving, we would expect fossils of different ages to just pile up on top of each other and be present everywhere in the ocean. We would expect to see older fossils near the bottom of ocean sediment and younger fossils near the top, which, according to the law of superposition, we do indeed see. But in addition, we also see that the fossils get older and older as you move farther away for a divergent plate boundary, signaling to us that some animals have died and then gotten farther and farther and farther away from the center of that boundary as the boundaries have moved over time. So we also have evidence in the fossil record that suggests that this is the case. If we have a divergent boundary underneath the ocean, we have a name for it. It's called a mid-ocean ridge. Okay. If we have a divergent boundary on land, it's called a rift valley. The mid-Atlantic ridge is a really good example of a mid-ocean ridge in the middle of the Atlantic Ocean, and there are rift valleys in eastern Africa where Africa is splitting apart from each other in a certain location. So those are some examples from real life about that. Just to wrap all this up together, divergent boundaries are creating new crust. Convergent boundaries are destroying crust. So this combination of convergent plate boundaries where plates are moving towards each other and divergent plate boundaries where the plates are moving away from each other means that crust is continually recycled as it moves on the surface of the Earth. If new crust is being created on one side of the Earth, it is being destroyed somewhere else at the same time. Thanks for watching. There are 2 other ways that plates can interact to make sure you get all 3 courses for today, convergent boundaries as well as transform boundaries. Be sure to answer the questions to summarize what you've learned from Plate 2, divergent boundaries and seafloor spreading. And thanks for watching this video.